Okay, great. Okay, so I'm going to actually switch back to the computer. I'm going to start by introducing some of the things you see that on the PowerPoint that give you sort of an overview and a review, and some basic, some other sort of basic vocabulary and skills we need to be successful with factoring as well. So if you are my online students listening to this, then follow along on the PowerPoint that is posted on my math lab, because that's what I'm referring to if it looks like just a blank screen right now. Okay. Okay. So this PowerPoint is actually a work in progress. I'm trying to make it very, very thorough and extensive. And so you're going to see things get changed and updated in it. It covers what we're covering in class today, and more will be added to it, and other things may be kind of tweaked as I see what information works for you guys. Okay, so I will post this in Unit 2 on my math lab, and I'll also make notes when I've updated it. Okay, so as we go along. Now, if you took 308, or even if you didn't, you still, the textbook we're using here is still the textbook that you're using now. Okay, so you can get a more thorough, it goes a little more thoroughly into factoring in the 308 material, and that's chapters 6.1 through 6.5. Okay. So you can always go back there and review with a little more information from those chapters. And in MATH0310, we cover it in a little quicker fashion in 9.1 to 9.3. We'll also do 9.4, but that's like applications and equation solving with these with factoring, using factoring. Okay. All right. So to start off with, some of the sort of knowledge you already need to have and understanding and vocabulary. Please, please, please make a point of whenever I use vocabulary, use certain words in class, if you don't know what I'm talking about, please ask me. Okay? This is, you're going to see some of the words I use over and over again are just really key foundational algebra terms. And I guarantee if you're asking, you're probably asking for about 5 other people that don't want to speak up. Okay? At the very least, I keep a pack of Post-its or something and write these words down. Look them up. Google at your fingertips. Okay? Or talk to me after class. Okay? So one basic understanding is polynomials. Now I'll post some of these in the Unit 2 as well, like review suggestions, but that's a 308 topic in 5.2. Okay? So understanding a polynomial. Polynomial is like the building blocks of algebra. Okay? So you can have any term. A term can look like anything. Okay? With x's and y's and z's and exponents that are, exponents themselves could be, positive numbers or negative numbers or fractions or decimals. Even exponents can be anything. You can, so anything that is a little like, product, a little number times a variable with or without an exponent is a term. And if you join these terms with addition and subtraction, you have an algebraic expression. But if we get a little more specific, what we're really concerned with, working with what we're working here, is polynomial terms. Okay? So polynomial terms have a little stricter rules. That is the basic form, algebraic form of a polynomial term, ax to the n. Every algebraic polynomial term is of that form. Okay? So for example, 3x or 7y squared. Okay? A is the coefficient. So a is a number, and a can be any real number. The coefficient can be any real number, including fractions, decimals, positive, negative, 0. Any real number. Not a problem for the coefficient. But in a polynomial term, n is restricted. N has to be a whole number. So what is a whole number? Is 8 a whole number? Yes. Is 0 a whole number? Is 1/2 a whole number? What about negative 3? Yeah. Only the the non-negative numbers. So 0, 1, 2, 3, 4, etc. Okay, so the counting number starting with 0. Now, negative 3 is part of a larger set of numbers that includes the whole numbers, but if you include the negative numbers as well, what do you have? Very important. Because I referred to this word often, it starts with an I. Integers, yeah. Integers include all those negative numbers as well. Not the in-between numbers, but 0, 1, 2, 3, 4, and also negative 1, negative 2, negative 3, negative 4, so infinity in both directions. Okay. Now you can have negative exponents. In fact, in 308, we talked about negative exponents. Okay. But for a polynomial term, so that a general term, just a term, can have a negative exponent, but not a polynomial term. Polynomial terms are always 0, 1, 2, 3, 4, but they're whole numbers. If you have a negative exponent, you actually have something called a rational term. And that's going to be chapter 10. That's coming up next. All right, so a polynomial is just a string of polynomial terms. They're joined with addition and subtraction. A polynomial is a sum of terms. When I say sum, that's the same thing as subtraction. Subtraction is just defined in terms of addition. Subtraction is just adding the opposite. So when I say sum, I mean both plus and minus. So there's an example of a 4-term polynomial. Okay. X to the 7th is one term. What is our, that, all of those are in the form ax to the n. For that first term, what's the a?
A real number.
It is a real number, but what is it? What is that number? 1. Yeah. If you don't have a coefficient, you actually do. It's a 1. You don't have to write it. You can put it in if you have to do some math with it. Huh? But that is 1x to the 7th. A is 1. What is n? 7. Yeah. A is a real number. 1 is a real number. 7 is a whole number. What is a on the second term? Negative 3. Right. Careful, because the sign, the operation in front will tell you the sign of it. So it's negative 3, and what is n? 5. Right. Now when you get to the end there, the last term, the 4th term, what is a? Negative 8. And what is n? 0, right. Because if I have x to the 0, what does anything raised to the 0 power equal? Raised to the 0 power. 9 to the 0 power, x to the 0 power.
I mean 0, because there's no x.
Well, if it equals 0, then x to the 0 would equal 0, and negative 8 times 0 would be 0, and then there wouldn't be a negative 8.
And it does stay by just...
Anything raised to the 0 power, and this will come up again in an example during later, but anything raised to the 0 power equals 1. So that last term, negative 8, is actually ax to the n. Your a is negative 8. Your x to the n is x to the 0. X to the 0 just equals 1. So negative 8 times 1, just negative 8. Now that's getting really technical and algebraic. The point is, though, if you see a constant is a polynomial term. Just a number is itself a polynomial term. So that's a 4-term polynomial, and they all technically have variables, though one of them is a constant to your eye. Technically, algebraically, it has a variable of x to the 0. Okay. And that x to the 0, that idea of the 0 exponent, has to do with our exponent rules. Okay. So this, you can review these in 5.1 from 308, and they're going to come up again in chapter 11 when we deal with radicals. Because radicals, like square root signs, are the opposite of exponents. Okay. So we're going to be doing, so I review a little bit with the exponent rules now, and go a little further with that in chapter 11. But you do need to know, and when you're dealing with polynomials, you're dealing with terms with exponents. So you need to have the basic rules for combining those. These are the rules you need to start having in your sleep. The basic exponent rules are the product, quotient, and power rule. And they require like bases. If this were an x and this were a y, you couldn't do anything. You can put them next to each other, you don't need the dot, but you couldn't smush their exponents together. So if you have like bases, and it's multiplication, product rule, multiplication, what do you do to the exponents? You add them. Because, for example, this means you have x is a factor 5 times, and here x is a factor 3 times. How many times is x a factor? 8 times. 5 plus 3. Common base of x, add the exponents. If your bases were different, you can't add the exponents, because what would your new base be? So it has to be a like base, so you keep that like base, add the exponent. The quotient rule, you are dividing. Quotient, division. And as long as the bases are alike, what do you do to the exponents?
Subtract.
Yeah. Because that's like canceling out. Okay? Anything over itself, it cancels out to 1, then you don't need it anymore. So, for example, x to the 7 over x to the 4th. 7x is on top, you're canceling out, taking away, subtracting 4x's on the bottom, leaving behind 3x's. The power rule is taking a term with an exponent, raising it to another exponent. And that means that a to the m is a base this many times. X cubed is a base this many times. So this is x cubed times 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 x, 8 times. So that's basically 3 plus 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 3. Or just 3 times 8. The power rule is just a shorthand way of doing the product rule. Okay? So power rule says multiply those exponents, because this x happens 3 times, 8 times. 3x is 8 times. Like I said, in 5.1, you can review those with a little more depth, but those are the basics. Those you should know in your sleep when you are dealing with polynomials, how you combine, multiply, and divide polynomials. Okay with this? Okay. So, all right. Another sort of basic skill, because what we're doing today, what we're doing working with factoring, is actually we're reversing the process of multiplying. That's all factoring is reversing multiplication. Okay? So, multiplying polynomials is the opposite of factoring polynomials. You can go in both directions. Okay? The two basic kinds of polynomial multiplication, distributing and foiling. We did plenty of distribution in the first unit. We did that to help clean up our equations before we solved them. Okay? So distribution is when you multiply a monomial, or specifically polynomial distribution. You can have any term. It doesn't have a monomial is just a polynomial term, one polynomial term. Okay? So you can have a non-polynomial term, but specifically polynomial distribution. You got a monomial and then times some other polynomial. And that polynomial, it could be a binomial, a trinomial, it could have any number of terms. But you distribute, you multiply that outside monomial times each term. What you are doing here is you are turning a product into a sum. We're going to reverse the process with factoring, go from a sum to a product. You've got how many factors here?
1, 2.
And 2, right. Anything that's locked up, that plus and minus doesn't matter there. If it's locked up, it's one chunk, it's one thing. Factor 1, factor 2. Okay? This is a product of 2 factors. So we're going from a product. When we distribute and unlock those parentheses, we have created a sum of 2 terms. Okay? So multiplying takes us from a product of factors to a sum of terms. These are the 2 factors. When you multiply them, you get a sum. In this case, a difference, but that's the same thing as a sum of these 2 terms. Now, foiling is just kind of this fancy distribution. Foiling is just kind of a little mind trick to help remember sort of the order so you don't miss anything. But basically, all we're doing here, foiling we use when we're multiplying a binomial times a binomial. Okay? We're still going from a product to a sum. Here's a binomial times a binomial. How many factors do we have? 2 binomials. Okay. And to FOIL them, that FOIL stands for first, outside, inside, last. Because all we're doing is distributing. First we distribute the 2x. 2x times 3x is the first 2 terms. Then we distribute the 2x to the 2, so that's the outside terms. Then we distribute the negative 5 to the 3x, that's the inside terms. And then the negative 5 times the 2, those are the last terms. FOIL. Right. Now, FOIL has how many letters? So you end up with 4 terms. Now, if your terms happen to be nice and and if your 2 factors happen to be where your first terms are like terms and your second terms are like terms, so these are both x's and these are both constants. Okay. So if you have like terms first and then like terms second, then you're going to get FOIL, 4 terms, but then because of that special setup, those middle 2 terms are going to end up being like terms, which then give a combined into 1. So you're always going to get 4 terms, but sometimes you can then actually turn it into a trinomial, a 3-term. Okay, you've got these 2 factors now, a binomial times a binomial, and when you multiply them and break up those parentheses, you turn a 2-factor product into a sum of 4 terms, which then was able to be simplified into 3 terms in this case. Okay, a sum or difference of these 3 terms. Okay with that? Okay. All we're doing with factoring is we are reversing that process. We are going to go from a sum, some polynomial, sum of terms, and we are going to break it into It's factors. Okay? We are going to undistribute, or we're going to unfoil and go in the other direction. So you can always check your work. Just like you can check your work with distribution, you can check your work with factoring by you can go both directions to check your work. With the okay. So polynomial factoring. You already have a sense of factoring numerically. For example, how can you, with multiplication, get the number 15?
5 times 3.
Right, 5 times 3, or 3 times 5. What's another way?
Okay, sometimes decimals.
No, it'll always be whole numbers, or integers, rather. Yeah.
15 times 1.
Yeah, or 1 times 15. They could also both be,
Negative.
yeah, negative 3 times negative 5, yeah. Or negative 1 times negative 15, yeah. So in that case, there's 2 basic factor pairs, but 4 if you consider the different sign combinations. Okay. So breaking 15 into numerical factors. You can break 15 into 3 times 5. Okay. Well, what's 3 times 5? So you check your work. It goes back both ways. You multiply 2 factors, 3 times 15, and you get 15. You take 15 and you break it into its factors, you get 3 times 5, for example. Okay. With polynomials, you're not going to have a whole list of them like, multiple factor pairs. You're going to break it into, there's going to be one answer, okay? But the same idea. You're taking a polynomial and you're breaking that polynomial, which is a sum, into its component factors, okay? Which will be a product. Then once it's factored, all the plus and minuses will be gone. Oh yeah, there'll be plus and minuses like locked up in parentheses, but there's not going to be any free floating outside the parentheses. It's going to be monomials or binomials or trinomials multiplied times each other. Okay. So factoring polynomials is the opposite of multiplying polynomials. And that's it, just reversing the process. So we're going from a sum to a product now, a sum of terms to a multiplication of factors. And here's I add this. We take a polynomial, and our job is to break it into linear, if possible, linear factors. Okay? Because the big thing, a lot of the factoring can be overwhelming because there's so many different techniques. And you look at a page of factoring, and you're like, the brain kind of freezes. Okay? So here's what I want you to keep in mind. What do I do first? And how do I know when I'm done? Okay? Well, the answer to what do I do first is always the same. I'm about to get into that. How do you know you're done? Because you might have more than one step. You might have to use more than one type of, you might not be able to factor at all. You might be able to only factor with one type set, or you might have 2 or 3 steps even. How do you know when you're done? You know you're done when you have nothing but linear factors. What do I mean by linear? How do you know if it's a linear factor?
It's the x without exponents.
Without exponents, right? Exponents of 1. Okay? Clean x. Just like when I'm talking about linear, solving a linear equation has an x with no exponents. Or graphing a linear equation with 2 variables, x and y are clean, no exponents. Those are linear. They make a line on a graph. Okay. Your factors, when you finish, should all be linear, no more exponents. You'll start off with some exponents in your polynomial, but you should end up with no more exponents. Each of your factors should be a little linear factor. If you have 2 factors, they should both be linear. 3 factors, you might end up with 2 or 3 or 4 factors, they should all be linear. Now that's not always possible. Sometimes something is not factorable. In fact, by the end of this course, we're going to start looking at things that aren't factorable and how you deal with those. Okay? So you might get to your factors and go, oh, I still have an exponent in that factor. If it's linear, you know you're done with it. It's part of the answer, but you're done with it. Anything that still has an exponent, you have to ask yourself, can I keep factoring? So how do you know when you're done? When there's no more exponents, or if you look at something with an exponent, like, no, it's prime. I can't do anything else with it. So I know there's an exponent there, but I know I'm also done because I can't. It's what's called prime. If you wanted, instead of 15, if you wanted to break 13 up with multiplication, what would a factor pair of 13 be?
13 times 1.
Yeah, what else?
Negative 13 times.
Yeah, aside from the negative version, your basic like positive factors, 1 times 13. 13 is a prime number. And the definition of prime is only 1 times itself. You can have prime polynomials too. And it's prime when it can't be factored anymore, when only 1 times itself. Okay? And linear factors are, once at least, unless there's a GCF, a numerical GCF to take out, linear factors are prime. In other words, you're done with them. Okay? And sometimes they have exponents, They're still prime, but you have to ask yourself. You have to check first. Okay? So that's how you know when you're done. Questions? Okay. So let's look at where we begin. Okay? So the other question before how do I know when I'm done? Where do I start? Because you look at a mixed page of factoring and there's so many different techniques. How do I start? The answer is always the same. If I remember, what's the first thing you should always do when you're asked to factor something? First step always. Yeah. And also GCF. I heard GCF from someone. Want to give credit? Okay. Yeah, GCF. Remember that? GCF? GCF. GCF is always the first thing. Sometimes that's all you can do. Okay? Sometimes you take out a GCF and you're done. But you don't know you're done until you take out that GCF and you look at what's left and there's no more exponents, or if there are exponents left, you're still done. Then you can't break it up anymore. It's prime. What's left over is prime. Okay? And you can't even decide in some cases what factoring technique to use next until you've pulled out a GCF, because you don't know what you're really looking at until the GCF is pulled out. Okay? So that is always the first term. Where you start, you ask yourself, is there a GCF? Okay? So the next thing on this is sort of breaking down that GCF. Now, GCF or GCD, it doesn't matter if they're capitalized or lowercase. Doesn't matter either one. And you might also see GCD. Just like addition and subtraction mean the same thing. Subtraction is just adding the opposite. Multiplication and division mean the same thing too. Division is just multiplying by the reciprocal. So factor in GCF is another way of saying GCD, which is divisor. Factors you multiply up, divisors what divides into the big number. Okay? I just put that GCD, I usually say GCF, GCDs in the calculator. I want you to know those are synonymous. Now, I got that double arrow there because you can go in both directions. Okay? Your basic GCF means you're taking some polynomial, and you're dividing out a monomial. You're dividing out a GCF. This is the opposite of distributing. So an informal math term, undistributing is all you're doing. And so you can always check your work with distribution. Okay? Now I'm going to switch over then to Zachary, and we're going to actually practice these. So we'll come back to this. But this is the basic breakdown of the very first thing you do and some things you might see. A numerical GCF, for example, those three terms, the biggest number they have in common that can be divided out of them is 2. Now what about, look, if you just look at the 8 and the 12, what can you divide out of 8 and 12? 4, right. But can you divide that out of 6? No. You have to be fair to every term. We always come back to that multiplication property of equality. And this gets back to solving linear equations. When you kill fractions, you are being fair to every term. Multiply every term by the LCD over 1. Okay? Divide both sides by the coefficient to finish solving a linear equation. Divide everything by the same number. This is all the multiplication property, which says you don't change the value of something as long as you treat it fairly. Okay? Every term. Okay? So I'm dividing out at 2. That 2 doesn't go away. That 2 is part of the answer. That 2 is a factor. It is the greatest common factor and is part of my answer. So it goes in, as soon as you pull out your GCF, you write it down, and you put up a parenthesis. I'm going to demonstrate that as we practice these. You put down your GCF, put up a parenthesis. It's like, that seems kind of like, it will look a little confusing in the next one, so I want that to be the practice. Pull out your GCF, do not forget about it. It's part of the answer, put up a parenthesis. How many factors, when we factor that trinomial there, how many factors are in our answer?
Is it just 1? Or 2?
2 is one of the, yeah, okay, so 2 is one of them, that's the GCF, and what's the other one?
The whole other.
Yeah, the leftover divided out trinomial. So that's a 3-term sum turned into a 2-factor product, a product of 2 factors. And these 2 factors, one of them is just a numerical GCF, and the other factor, or a monomial, and the other factor is a polynomial, specifically a trinomial. Okay. And you might be pulling out that number, a variable. When you pull out a variable, you got, for example, x to the 7th, x to the 5th, x cubed, and x squared. What's the most they have in common? How many x's? They all have at least, we got 2. X to the 7th, x to the 5th, x cubed, x squared. They all have at least 2. You can't pull out more than that because then you're going to leave an x on the bottom. You can pull out 3 from the first 3 terms, but not from that last one. Okay? So when you're pulling out a variable, that's because they have a common like base, and you pull out the most that they have in common, which is the smallest exponent. And there's our quotient rule. X to the 7th divided by x squared. There's our GCF. When we divide that out, 7 minus 2 leaves behind x to the 5th. If you redistribute this to check your work, that's what the arrow is going in both directions. X squared times x to the 5th, that's multiplication. Product rule, what do I do to the exponents? Add. Goes back to x to the 7th. Check. Sometimes you'll have a number and a variable, and then also it's often the case where you'll want to factor out a negative GCF, either just a negative sign by pulling out -1, or other stuff too, but a negative version instead of the positive version. So we'll look at those instances. So let's get our hands dirty now, put pencil to paper, and we'll come back then to what we do with that moving forward. Oh, question? Oh, I thought I heard a... Oh, okay. Don't worry, I'm going to post this PowerPoint. Okay, you don't have to copy everything down off of that. It'll be posted so you can go back and review it and so forth. Yes, I'll be updating and reviewing, posting it and updating it regularly throughout this unit as we do new stuff or as I get new ideas from you guys what should be on there. So, here are my guinea pigs. All right. So, okay. So, as you get more fluent and comfortable with all different types of factoring, there are steps that you can absolutely do mentally. Make sure you're comfortable and you have your strategies in place before you start seeing things that you can leave off the paper. So what I'm going to do here is sort of visually how you can organize it as a strategy, and then as you move forward, you'll find your own strategies or find things that you can just do more efficiently mentally. So 3x minus 21 xy to the 4th. How many terms? 2, yeah. This is a 2-term polynomial. So I want to see if they have anything in common that I can divide out of both of them. I look at the numbers first, 3 and 21. 7 will come out of 21, but not 3. Yeah, so the biggest one that will come out of both of them is 3. So I can put a line, there's my 2 terms, so 2 lines. And the biggest number that will divide out of both of them is 3. Your numerical GCF cannot be bigger than any of the numbers. So it's either the same size or smaller than the smallest one. Just like a least common denominator is the biggest one or bigger, a factor is the smallest one or smaller. So pull a 3. Now let's look at the variables. We can look at x's. Do they have any x's in common?
Yes.
Yeah, and the most they have in common is? Yeah, 1 each. Yeah. So there's exponents of 1. They have that in common. What about y's? No. This has y to the 4th, but this doesn't have a y. They're not in common, so it's not part of our GCF. Okay. Now, that is one of your factors, 3x. Now, is this factor linear? Yeah, it's an exponent of 1. It's linear. It's done. You're done with it. There's nothing else to do with it. It's part of the final answer. Don't drop it, but you're done with it. So as soon as you pull out your GCF, immediately put up the parenthesis. Because factors, remember, are multiplication. So this is your GCF times something left over. Okay? So you divide out to find what that is. 3x divided by 3x. It cancels into 1, right. It's not blank and it's not a 0. Any number or term over itself equals 1. You can't just put a 0 or leave it blank. This equals 1. If there's something else there, you don't have to write the 1. But if there's nothing else, it's just a 1. Now, I don't worry about whether my tops and bottoms are negative or positive. I make a point. My strategy is to just make a point. Okay, this is a this is a positive one, and here I've got a negative and a positive. So I know it's just going to be subtraction. So I always just mark what my operation is, and then I just do 21 divided by 3. What about the x's? Yeah, just like those 3's and x's cancel out. These x's cancel.